Christin Ford is our senior lead applications engineer from Superior Essex. Christin knows what she's doing. When I don't know what I'm doing, I lean on Christin heavily, and she always helps out. So again, it's a lost opportunity. If you don't get a chance to meet some of your counterparts in the room, you can say that we're competitors. There's no one's a competitor. This is the world. If you have a question, please ask it. We had some questions between the presentations that are outstanding. And again, Christin will be here for a while. So with that, I'll pass it on to Christin.
Thank you very much. And Rick already had some good questions that hopefully I'll cover in this presentation. But I really appreciate your time and for you to join me today. So today we're going to talk about power over Ethernet, just to get a baseline, and we're going to talk about where we're using power over Ethernet, the impacts of high PoE on your LAN, and then using those topics as a baseline to understand how to get further reach from our copper data cables. They're all pretty important concepts in understanding how far we can actually reach. And then case studies if we have enough time. Okay, so what is power over Ethernet? Power over Ethernet, we also call it PoE, and we're transmitting both data and power down the same copper twisted pair cable. And it consists of power sourcing equipment and a powered device, and those are connected by your copper data cables. The IEEE defines the PoE standards, and there's 4 types. There's types 1, 2, 3, and 4, and they're injecting power of roughly 15, 30, 60, and 90 watts of power. But more importantly, IEEE defines the minimum power that needs to reach the powered device. Because as you inject power, there's loss at the connection points, and there's also loss as you have voltage drop down that cable, and that needs to be accounted for. So the most important value is actually how much power reaches that end device, because if enough power doesn't reach it, it doesn't work. So originally, the IEEE came out with standard 802.3 AF for PoE, and it involved injecting a max of 15.4 watts of DC power. And then IEEE 802.3 AT came out in 2009. We called that PoE Plus, and that can inject up to 30 watts of power at the source. So these are called types 1 and types 2 PoE. And they're enough power to power something like, say, a voice over an IP phone, some wireless access points, some cameras. But there was a big drive for more power. So IEEE 802 came out with .3 BT. Let me jump back to types 1 and type 2 real fast. Those are transmitting power over 2 of the 4 copper pairs. But the industry had a need to grow the application and provide more power. So at the end of 2018, they came out with 802.3 BT, which describes how to inject 60 watts and 90 watts of power. And that type of PoE can deliver enough power for multi-radio wireless access points, point-tilt zoom cameras, video conferencing type stuff. So it really increased the applications that PoE can drive. We call types 3 and types 4 4-pair PoE because we're getting that additional power by now transmitting power over all 4 pairs. So the power and the data are coming over all 4 pairs now. And we call it 4-pair PoE, PoE++, UPoE, and high PoE. Now I'm going to be calling it high PoE throughout this presentation. So when you hear me talk about high PoE, I'm talking about types 3 and 4, the injection of 60 and 90 watts of power. One of the reasons we call it high PoE is because it's starting to generate a whole lot of heat. And heat ends up an incredibly large factor in all of this. As Corey already mentioned, heat is going to be a big topic, and I'm going to spend a lot of time talking about heat and heat mitigation. the standards that cover power over Ethernet are the IEEE, as we just discussed. It's covering both the data and the physical link. And then we've got best practices covered in TIA and in BICSI standards. So TIA, TSB, or Technical Service Bulletin 184, specifically addresses sending power over Ethernet over copper twisted pair cabling. And it especially addresses the heat rise and heat mitigation and bundle sizing recommendations. And then BICSI 005 talks about electronic safety, and 007 talks about intelligent buildings and premises. Those are all standards, so they're best practices. Then you have code, and code is something you have to follow because it's driven around safety issues. And the safety over POE is defined, in NEC NFPA 70. So somebody bounce back to me, over how many pairs does a type 4 POE device transmit power? You got it, y'all are smart, good job. So now let's talk about where we're using POE. How are we using it? We're using POE-enabled end devices to operate off that single communication cable instead of separate power and data cables. And we're using POE to enable smart buildings. So smart buildings is a convergence of typically disparate, analog, and proprietary building systems. We converge all those systems onto a single network. So this allows the integration and the control of the building, and even the automation where the environment starts to learn from the data that it's collecting and making the building more efficient and making improvement. So POE and the end devices that are enabled to run off of POE are making buildings become smart. So for those of you who have been doing this a while, think back about how a typical LAN looked way back when. And then here's a real world scenario of one that was pretty recent. You've got a 2,300 square meter floor plan, and now you have over 800 devices connected with POE cabling. So you can see the desire of people to connect things over POE. And this is pretty typical now. When we say that we're ready to make a building smart, we're really ready now. There is a POE-enabled end device out there for pretty much anything that you'd want to do. And now that POE has gone up to 802.3 BT, or injecting up to 90 watts of power, it's encompassing even more functions. So in the building services, we've got things like wireless access points, ceiling fans, smoke alarms. In our security field, we've got surveillance cameras, facial recognition, IP call towers. Workspace, we have curtain motors, we've got light fixtures, POE displays, all kinds of good things. But one of the limiting factors here used to be supplying enough power to make all these things function. So the standards needed to work out how to safely transmit and reliably transmit power over a communication data cable, and the device manufacturers had to come up with a way to continually make the end devices more and more efficient so that they could run off of 90 watts or less. So for instance, who would have ever thought in a hotel room that you would see a hotel mini fridge being powered off of a power over Ethernet cable, a 5E cable with RJ45s or 8P8Cs? But it's happening today. And with the ability to merge the operation and the monitoring of these systems together, it makes everything more efficient. So smart buildings enhance an occupant's satisfaction. Let's imagine that you've got a hotel customer, and maybe she's put in her preferences in her loyalty program app. Or maybe she's visited enough of these smart buildings that the building has actually learned through her habits what her preferences are. So let's say that she likes 77 degrees, she likes the blinds open and the lights bright, she likes it nice and bright. Let's say that she likes to have the TV turned on to the Weather Channel with a little ambient noise. So when she comes into the hotel, either she's checking in through her app or checking into the front desk, or maybe even in this smart building, it's recognizing her through a facial recognition software program. She sees she's coming, and it makes her room 77 degrees with the blinds open, the lights on, and the TV turned to the Weather Channel at a low volume, just like she likes it, so that her home away from home is actually that, a home away from home. It's more comfortable for her. You can even set the water temperature in the shower to her liking. So all that's possible through PoE. So smart buildings can improve, they can improve lighting, they can improve the security functions in a building, they can improve the indoor air quality through things like fresh air cycling, and in times where we've got pandemics and coughing going around, fresh air cycling is a pretty important thing. Now the building owners are also seeing the benefit of smart buildings. So they're not only seeing the benefits of this through reduced CapEx and OpEx, but they're seeing reduced installation costs. They're not only installing just the data cable, but they're not installing power cables now, which means there's less materials, and that means less conduit. It also means you have to have less power outlets as well. So if you've reduced your CapEx, and your installation costs are lower because you don't have to have a high voltage guy install this. And in this day of labor shortages, that's pretty important. Also, because the end device manufacturers have worked to make all these end devices more power efficient, add that with sensors and software that can also optimize energy usage, and you're reducing your OpEx. And whether you look at this through a lens of sustainability or not, what it translates to is lower power bills, which everybody likes. And because you need less cabling, and because these systems are all converged on a single network, you can actually reduce your IDF and electrical closet space. And what can you do with that additional space? Make it into more money generating space. For instance, there's a hotel in Texas that went all smart building, and they were able to reduce their IDF and electrical closet space by half. And they turned that additional space into more rentable rooms, so it made the building more valuable because they're now using that space as more money generating space. Also, with a PoE smart building, if your power goes out, if your system is backed up by a UPS, your power's still on and your devices are still running when the rest of the block is out. So not only are the building occupants seeing a benefit, but the building owners are as well, all while supporting the environment. So power consumption today, linked to ITC, accounts for about 5 to 9% of the world's total energy consumption. That's a big deal, and it's growing. So today, the industry is asking, how is this energy produced? How is it managed? And what's the environmental impact? And smart buildings is an answer to this. So in addition to supporting more people, the world's buildings are facing increased demands for greater productivity and profitability, while still addressing the world's environmental concerns. 40% of the world's global carbon emissions are a result of buildings. That means there's a lot of room for improvement to make buildings more efficient, especially office buildings. So if you were to bring PoE enable smart buildings, a hospital and retail store could expect to see a reduction in energy consumption by almost 15%, hotel buildings by almost 7%, and office buildings by almost 20%. So how do we deploy PoE infrastructure to make a building smart? So imagine the building, the actual bricks and mortar of a building, as a piece of hardware like your smartphone. And then imagine that this PoE LAN cabling system is the operating system on that smartphone. And imagine all these end devices that you're putting onto the PoE system are like the apps on your smartphone. So they can be plug and play, they can be changed, they can be upgraded, but you've got to have that operating system first, and that's where the PoE LAN comes into play. Our customers want to take advantage of the efficiencies, the automation, and the intelligence offered in a smart building. But today that's very complicated because, again, these building systems are operating on their own proprietary, disparate analog systems. But the future state is going to allow convergence, and it's going to eliminate waste because everything's going to be working off of a common software platform. So we're going to break down those silos to increase efficiencies and partner that with AI software, and the building actually starts to learn from the data it's collecting and become more smart and more efficient. So in addition to the simplification, PoE is cost effective, it's more reliable, and it has an incredibly broad set of applications that are revolutionizing smart buildings. And all of this is done with the same structured cabling system that we've been using for years, the same switches we've been using for years, like with voice over IP. So we know it's reliable, we know it's safe. And then the switches can also be added for redundancy. They can be stacked. So not only is a PoE deployment reduce installation costs, use less materials, etc., but deploying PoE offers a range of other sustainable attributes from occupant wellness, carbon reduction based on enhanced energy efficiencies, and also can provide LEED credits for the EA category of LEED, the energy and atmospheric category of LEED. When you're making the infrastructure for a smart building, you need to make some cabling choices. Bixby is going to tell you that you need to go all 6A for future proofing, but does that always make sense? Maybe not. Think about the application and think about the budget that you have. Imagine that you've got a sensor that runs off PoE, and imagine that sensor takes a whole 4 watts of power to operate and runs off maybe 2 megabits per second of data. Running a Cat6A cable that easily handles 10 gigabits of data per second seems a little bit overkill and quite honestly a little bit too costly. So maybe you balance the budget of your project with the application of where you're running these cables. If your main goal is future proofing, sure, go all 6A. But if you've got budget constraints and you've got room to think about this, think about maybe mixing it up a little. So if smart buildings are so smart, should we be changing our homes into smart buildings? Any thoughts? It sounds really neat, but who has switches in an IT closet in their house? Switches are pretty expensive, and we typically don't have IT departments at our house, unless it's you. So in small scale applications, probably not the way to go. But for places like hospitals and retail stores and office buildings where you've already got these network switches, you've already got an IT department, so large scale MDUs or deep retrofits, this totally makes sense, but maybe not so much on smaller scales. So how are the components of a LAN network designed to support high PoE? And just as a reminder, when I talk about high PoE, I'm talking about injecting 60 and 90 watts of power, and that creates high temperatures. Temperature is a huge concern with our LANs. High PoE creates higher temperatures. Higher temperatures create attenuation, and attenuation means that you've got signal loss. When you have signal loss, that means you need to deploy shorter and shorter channels to make this work. As you get higher temperatures, you've got to decrease your length. The data on the right is actually one that Corey showed, so the next couple slides actually mimic what Corey was saying, but I'm going to go a little bit deeper into them. So thank you for that emphasis. And I'm going to be called Rethunder now too. Me and Eric are going to be called Rethunder. So this data right here is of the temperature rise of a 100 cable bundle. You're going to notice a pretty dramatic line here, but we studied various categories, gauges, and quality of materials. And the first thing we noticed is category isn't a factor in this at all. But gauge and the quality of materials are hugely important. For instance, this pretty dramatic line here was a cable that our lab ordered off the internet, and it was marketed as high PoE ready. And just as Corey mentioned with his customer, they have nice language to make it sound like it's good to go. When we got it into the lab, guess what? It had copper-clad aluminum conductors. Please don't ever use copper-clad aluminum with high PoE. It's not only a safety issue, but causes extreme performance issues as well. So we said, well, we got this cable, let's plug it up and see how it compares. So we plugged it up and we started to raise the temperature to simulate high PoE transmission, and it started to melt and fuse together. And we ripped it out of the wall before it started a fire. So that's a pretty dramatic example, but a very real-world example of how choosing cheapy parts can be a real detriment and a huge safety factor when you're talking about high PoE. So you've got some cable design considerations when you're talking about PoE and heat mitigation. So let's talk about some of those cable design factors that help mitigate heat. The number one factor is gauge size. The larger the gauge, the less resistance, so the less heat is generated, so less loss. Again, the larger the gauge, the less heat. So the gauge size is the number one determining factor in making a cable more energy efficient and in mitigating heat rise. The cable size is also a factor in heat mitigation, as well as the quality of the materials. For instance, the temperature rating of the materials. Not only the copper-clad aluminum being a quality of material, but also the insulating and the jacketing material as well. And then another design element in heat mitigation is the use of shielding or other heat dissipating elements. And I'm going to show you a study in a minute that shows how shielding can also help dissipate some of that heat out of your system. So this data, well, this picture right here is of a cable that is not optimized for PoE, high PoE, or it's not optimized for constant heat exposure. Back in the day, you used to just transmit data over a communication cable, right? You didn't transmit power. So why in the heck would we design a cable and add additional cost to mitigate heat? Because data doesn't generate the heat that PoE does. So you wouldn't want to bump up the copper size and introduce this extra cost to your customers to bump up the copper size and to use heat mitigating or heat tolerant materials that are more expensive if you're sending non-heat generating data down the cable. But now we're sending power as well, and so this is a very important factor. So this picture is of a cable not designed to tolerate constant exposure to heat. So when we tested this in the lab, we took this cable and we heated it up at 120 C for 10 days, and you can see that the insulating material just crumbled away. So that's, again, a huge safety factor. Now UL, this is just some food for thought here, UL allows a cable's temperature rating to be based on the jacketing material alone. But you can see that the heat from high PoE touches it's coming from the conductor, it's certainly touching the insulating material first, isn't it? So maybe a little bit of a oversight in UL standards. just some food for thought there. Now, here's another demonstration of the cable design factors that I was just talking about. And this is, again, all really important in understanding how to get further reach out of a cable if we understand these heat mitigating factors. So take this last column, the Cat6 23 gauge UTP column, and use that as our baseline. We took 100 meter bundles and we powered them for 5 days. Now, over those 5 days, the Cat6 UTP 23 gauge cable, the temperature rose 20 degrees. Take a 6A with the same gauge size, but we've added a foil shield, the temperature rose 7 degrees less. Take that foil shield away, but bump up the copper size with the 5E+, now the temperature has only risen half of what the 23 gauge with no shield rose. So you can see that having a foil shield does help wick some of that heat away, but it doesn't have as much effect as bumping up the copper size. So even with the same gauge size, a shield is going to help mitigate some heat, but not so much as bumping up that copper to 22 gauge. So now let's look at the energy savings line here. Using that Cat6 23 gauge UTP as a baseline, powering that over 5 days, the Cat6A 23 gauge with a foil shield used 90 watts less power to do the same amount of work as the UTP version. Drop that shield again, but bump up the copper, and that 5E with the 22 gauge used 300 watts less power to do the same amount of work over those 5 days. Why do we care? What does that mean? Savings on your power bill, and everybody loves that. You got less heat because larger gauges have less resistance, and so you've got less loss, and it's more efficient transfer of power, which means lower power bills. All right, so LP time. And Corey was talking about this too. Cable heat is compounded when you bundle cables together in intimate contact, like what you'd see in a cable tray or in a conduit. This can become a safety issue as the heat rise is compounded. So the NEC came up with some rules about bundle sizes. But Corey already showed you, and I'm about to show you again, bore you with that eye chart. That table's a little bit confusing to look at. And usually people don't want to figure that stuff out. So UL came up with an LP listing that certifies if a cable has an LP listing, then it's robust enough to be exposed to the heat rise of any size bundle. So if it gets the LP listing, no bundle size calculations are necessary. Those cables can be bundled at will or to the Bixby conduit fill ratio, basically the installation worst case scenario. No bundle size calculations are needed. What LP stands for is limited power. And what UL does to test this is they take a 192 cable bundle and they put a thermocouple in the center cable and then throughout the bundle layers. And then they inject power, like 100 watts or 120 watts, and they're simulating that. They're injecting like half an amp or 0.6 amps all the way up to 0.9 amps to simulate this high PoE. And then they measure the temperature rise over those cables. Then they look at the cable rating of that cable, which is based off the jacketing material's operating temperature range. If the temperature rise, as they're injecting power, goes over that cable temperature rating, then it fails and it doesn't get the LP listing. But if the temperature rise is somewhere less than that cable operating temp, then it gets the LP listing. So here's that eye chart again. If you don't have the LP listing, then you need to go to this eye chart where you need to understand, what do I need to look at to get my cable bundle size? What can be approved as a safe bundle size? And this is a safety standard, a safety code. It has nothing to do with performance, but is about safety. What can safely endure this heat rise from this bundling? So you take your cable print string and you're gonna find the gauge of the cable written in the print string, and you're also gonna find the temperature rating of the jacket material. And you take those and compare it to the ampacity chart in this table to determine your bundle size. Now again, remember, UL allows you to print, or allows cable manufacturers to print the operating temperature of that cable based on the jacketing material alone. So possibly think about using a manufacturer that might use the more limiting of both the insulation and the jacketing materials operating temps, and putting that more limiting value on the cable despite UL allowing only the jacket temperature to be listed. Now, I'm not going to beat connectivity into the ground. We got 2 connectivity guys, but this is part of the discussion and how far we can get with extended distance. Corey's already talked about how when you've got PoE, you're going to have arcing. It's going to create those corroded spots, and you don't want your power and your data transmission happening on that corroded area. So it's very important to pick connectivity that has been engineered to make sure that when the connector is fully mated, that it's transmitting that power and the data on a nice spot instead of that corroded spot for the integrity and efficiency of that data and power transmission. Guess what another factor is with connectivity? Our good friend heat. Heat. Is that ringing a bell to anybody? We've got heat problems. So again, with connectivity, think about a connector that has been designed with a body cavity that allows maximum airflow to help dissipate that heat away. And maybe one that's built with headroom in there, because that IEC standard allows the 1 amp per circuit trace, and the IEEE 802.3 PT specifying 960 milliamps, it's not a lot of headroom. So maybe consider connectivity that's been designed with a little bit more headroom for safety there. All right, what's the most important cable design factor for limiting both heat and increasing the efficient transfer of power? What's the most important cable design factor? Gauge size, thank you very much. So materials are also very important, but the #1 factor in limiting heat rise and increasing efficient transfer of energy is gauge. Larger gauges, less resistance, less heat. So now let's get into power over Ethernet in extended distances. By extended distances, what I'm talking about, just to make sure we're all on the same page, TIA specifies that you can't go longer than 100 meters in a channel or 90 meters permanent link over 4-pair copper twisted cable. So when we're talking about extended distances, we're talking about going beyond that. Does a cable magically quit working at 101 meters? No, but it means that the standards haven't worked it all out yet. So some of the myths revolving around this topic are very general claims, vague claims that are not backed up by supporting data. They claim that higher categories can actually go further in distance. After all, you might think a Cat 5e cable is good, a Cat 6 cable is better than that, and a Cat 6a is even better than a Cat 6, electrically speaking. So if I want to go further, why would a Cat 6a, the best cable, not get me further? But it actually doesn't work that way, and we'll talk about that. So the claim about higher category ratings getting you further claims that a fluke test or other vendor manufacturer field test unit is going to tell you that your system will work much like a TIA test limit will in that field tester, and claims that extended distance can provide future proofing. So let's address some of these myths. why are we stuck in the standards being based at 100 meters when we know that it's not a dead stopping point? At 101, we still may work. But we're stuck there because the standards have worked out that if you are standards compliant, if you fit this set of parameters, it makes sure that your system will have the performance that is guaranteed and will be interoperable with everybody's equipment. So you know that if you have power sourcing equipment and your power device is standards compliant, and your cabling standards compliant, and your connectivity and your patch cords are all standards compliant, all the accessories are standards compliant, and you put it together per the recipe spelled out from TIA, it's gonna work. You can take it for granted and you don't have to think about it. It's more plug and play. And that's because a whole lot of research was done in the background to make sure that it can be super interoperable and make sure that the performance is there. But again, does that mean that the system won't work at 101 meters? No, it just means there's a lot of variables out there that we need to look at and see, like, will it work? Maybe, maybe not. About 10% of our customers run into distance constraints. Waiting on standards to be written about this stuff would take forever. And there are currently 0 standards out there today written about how to deploy in an extended distance. So this is a little bit Wild West. You've got to consider, how much data does my end device need? How much power does my end device need? What configuration am I going to be deploying? How much extra length am I going to be asking of this system? And how much heat is going to be generated if I'm running high PoE, and how much will that be a detriment to how far I can get? That's a lot of factors for you guys to consider. That's a whole lot. Certainly, TIA is going to tell you, if you've got something over 100 meters, build another IDF. That can be expensive, and who's going to give you the space for it? You could also go fiber. It's pretty much on limitless bandwidth, but it's still a little bit more expensive option because you've still got to figure out the powering of that fiber as well. So why not, let's see if we can make the more cost-effective copper solution work with a balance of the variables at play. This is not a matter of category. In fact, once you go beyond 100 meters, there is no category. The definition of category is electrical performance of a cable to a max distance of 100-meter channel. So once you go beyond that 100 meters, there is no category. Also, let's talk about category compliant cables. Cat 5e cable's good, 6 cable's better, 6A cable's even better than that. How do we get that optimized electrical performance? We do that by optimizing materials, but also the biggest factor is the twist play. And we optimize that electrical performance from 5E to 6 to 6A by making tighter and tighter twists. So imagine that in TIA compliant lengths, because again, there is no category beyond 100 meters. So in TIA compliant lengths, if you had a cable designed for 5E versus 6A, and you inject a signal down those cables at the same time, the signal that's injected into the 6A cable has got to travel down a very tightly twisted pair under the same jacket length. Inject that same signal under a 5E, it's got to travel a much less distance relative to a tightly twisted Cat 6A design. So when you're talking about your goal being, I want to reach further, having that optimized electrical performance in TIA compliant lengths is actually detrimental to getting you there if you have a Cat 6A designed type cable. So this is application driven. Also, most end devices don't need 10 gigabits per second of data. Most applications need 1 gigabit per second or even less, most of them like 100 megabits. Because mostly what we're seeing this is like installing, let's say, everything's in compliance, but you got 1 or 2 security cameras out there that won't reach, you know, and I don't want to build an IDF for it. A security camera is not going to need a full 10 gigabits per second of data. So having a relatively looser twisted cable is going to help you get further. Propagation delay and delay skew are also very important factors in determining how far you can get. So we have no standards out on the market about how to deploy PoE extended distance. We also have no way to test this. There are currently no field testers or even lab-grade equipment that can test both data and power throughput at the same time. So how do we sort through all this conflicting messaging? There is a piece of expensive lab-grade equipment called a bit error rate tester, or BERT, and it can actually simulate true network traffic. So you can tell it send a full 1 gigabit per second of data, and it's going to send 1 gigabit per second of data down that cable. And that's the only way to tell how far a signal can truly travel. But it still doesn't marry up with how does that partner with the heat rise from high PoE. So there's, again, no field or lab-grade equipment that can test both data and the effects of the power and the heat generated from that power at the same time. So what can we do there? We could take the cable and we could artificially heat it up in an environmental chamber to simulate the transmission of high PoE. And then while that cable's heated up, we can send the network traffic through that BERT tester. And then we can determine the throughput there. You also need to consider what configurations are you deploying. Are you deploying a permanent link, a 1 connector, a 2 connector channel? Because every connection point within your system is a point of loss. You need to determine what does your end equipment actually need as far as data and power. And then how efficient is your cable? Because we know that larger gauge sizes are more efficient, generate less heat. And is that cable warranted to extended distances? And are those warranties backed by third-party certified data? So we partnered with UL Solutions to determine which of these general claims are myths and which ones are actual factors in achieving extended distances over 4-pair copper cables over a 100-meter channel. And we tested 22 gauge UTP cables in 3 different topologies, the permanent link, the 1 connector, and the 2 connector channels. And we compared these horizontal cables, one made with a more tight twist that would be equivalent in TIA compliant links to a 6A design, or one that supports 10G base T, and then one made with a relatively looser twist, one that would be more centered around 1G base T applications. And then we also looked at patch cords, various gauges, stranded patch cords versus solid, to see how that affected the system as well. So if you'll recall, there is no field nor lab equipment that can test both data and power throughput. So we did exactly what I just described. We put our cable into an environmental chamber, and we heated those cables up to simulate that high PoE transmission, and then connected the BERT machine to it to send true network traffic down that cable at the same time. And then here are our findings. So this one in particular shows the permanent link or direct attach configuration. And you're going to notice that the cable that was designed, optimized for 10G base T protocols, goes a lot shorter than a cable designed with twists around 1G base T. And you'll notice that the 1G base T even can support up to 5G base T, even in extended distance. And you need to look at the power requirements and the data requirements and marry those up to understand how far you can get. And then here's the 1 connector channel. You're going to notice that the distances here are reduced from the permanent link slide that I just showed you, because you've got another connection point, and every connection point is going to add some loss. And you'll also notice that we've started to add patch cords here, and that we're comparing the 24 gauge stranded versus 22 gauge solid. And you're going to see that at this particular slide, it's not making so much difference. But you'll notice on the next slide, as we ask more and more of the system, that the quality of signal sent down a stranded patch cord versus a 22 gauge solid patch cord, those factors do start to compound and they do start to make a difference in how far you can reach. And then here's the same thing for the 2 connector channel configuration. You're going to notice that the links are just a little bit shorter than the previous 2 slides, because guess what? We've got another connection point, and every connection point adds a loss. So the test results at UL Laboratories, based on our methodology, proved that the heat generated by the different types of PoE signal does significantly impact the extended distance supported up to 20 meters less. We also noticed that there's no difference in distances between the 1G base T and 2.5G base T protocols at ambient temperature, and ambient temperature simulated the type 1 and type 2 PoE because they're not really generating so much heat. And you only started to see a difference with type 1, type 2 PoE at 5 gigabits per second in reduced distances. And then as soon as you use the 2 connector channel, you're going to start noticing significant differences in the differences of horizontal cable and patch cords with the different protocols. So we proved the impact of heat on data transmission and on aging of materials, the impact of the higher gauge cable for power efficiency and heat mitigation, the impact of using the right connectivity components in your network. And because so many variables are being balanced, a system may work for one device, but if you went and switched it out for a device that required more power or more data later, it may not work at that distance. So this really isn't a future-proofed application, it's more of an engineered solution. Now, once we started publishing this data, the market actually started asking us, we've got a lot of these things that we want to run out to one camera outside. How are we going to protect that from lightning strikes? We were like, that's a great question. How is surge protection going to add to this data that we just produced? So based on that market feedback, we started furthering our studies, and that's the next step that we're doing. And we hope to have something published for the next BICSI. All we know right now is generically that adding surge protection to this picture does decrease the guaranteed values, but by how much we don't know yet, because we've been testing quite a few vendors, and even within vendors, different part numbers within the same vendor, and we're noticing that there's a big discrepancy amongst vendors, so we haven't really been able to pinpoint a generic claim that surge protection will affect these guaranteed distances by X amount, but we're working on it, and we're going to try and publish something by next BICSI. Now, how do you know how much data and power your end device actually needs? Your customers might come to you and say, I want to connect this to extended distance, and I want to connect this camera that has 4 megapixels. It's got a rating of 4 megapixels. That's great, but it doesn't tell me anything. It might tell me the clarity of the image, but it doesn't tell me how much data is required to get that clarity of image. So you're going to look at the detailed cut sheet of your end device, and you're going to look for something with a unit of measure of megabits per second, gigabits per second, or X base T. And that's going to tell you how much data is required of the end device. So in this particular example, the network demands are going to be 10/100 base T. Use the most conservative value there. So go with, at most, this device is going to require 100 megabits per second of data. Then you need to know how much power that device is using. And you can find that in an environmental and electrical section, or maybe just a subsection called power. And here you see in this example that this camera is going to require a typical power of 5 watts and a max power of 6.4. So again, use the maximum value to get the most conservative estimate, and you're going to know that this device requires 6.4 watts max power. Sometimes when the infrared camera goes on, it really draws a lot more power, and that's where that max value comes in. So you take those values and you're going to see that this is a type 1 PoE device. And again, back to the very beginning of the talk, don't look at PoE types based on the injection of power, but how much power needs to be received at that end device to work. So we know that this one's type 1, because type 1 injects 15.4 watts of DC power on each port, and the type 1 end devices need to receive up to 12.95 watts. So this is a type 1 PoE device. When you're installing these extended distances, how do you test it? Because again, there's no field tester or even lab grade equipment that can test power and data throughput at the same time. If you have a PoE extended distance run and you need to test it, if you test it per TIA limits, it's going to fail for length and insertion loss. It has to, because you've gone beyond the TIA limits. But your end user does not want to see a test report that says fail. So what do we do? Manufacturers have entered custom specs into Fluke and AEM and Softing, all the various field testing equipment. These custom limits, how they're different from the TIA limits, is that they turn the length-dependent parameters to information only. So now your insertion loss, it just gives you a value. It doesn't say pass or fail anymore. It's just saying information only. It will leave on parameters that are not length dependent, like return loss or near-end crosstalk. Those parameters are only telling you that your system is connected well. Does that tell you that your system will work like a TIA pass would? Nope, it sure doesn't, because again, there's no field equipment that will do that. So, if all your testing is telling you is that you're connected well, that's where it's really important to have third-party verified testing backing up the extended distance claims, because this field tester's not really telling you that. You want to make sure you're working with a cable manufacturer that feels confident enough in their third-party verified data to say, if you have connected this system well, I'm going to guarantee our claims of extended distance. So, does a higher category cable give you longer achievable distances beyond TIA's 100 meter? I see a head shaking no. Very good. It does not. Number one, there is no category beyond 100 meters. And number two, a cable in TIA compliant lengths that's designed with tighter twists is actually your enemy here. If your goal is to get further, a looser, relatively looser twisted design is going to get you there further. Now, if you've been to Bixie, you've probably heard about, how am I doing on time? Am I okay? Close? Should I wrap this up? Okay. I can skip this video. Should I skip the video? It's a minute and a half. Yep, okay. Okay, just making sure. So if you've been to Bixie, you've probably heard about the Sinclair Hotel a lot. That was the picture here, and it went all PoE smart building. But here is another example, the Cisco Hotel.
Everything in this building is PoE powered. How are we doing all this?
So it's 10 switches, 240 ports, but each one of these is now 90 watts. All the power for the lights and the shades and all the control elements from this side of the building, it all collapses back here. This is that digital view of the 44,000 feet that we're standing in right now. So from an employee standpoint, we'll start our day here and actually, Sal, let's go book a space.
I get some data here too. So I get the room air quality, the temperature, the humidity, you make sure there's no people in here.
Power over Ethernet does not require to be run in pipe and conduit. So we're able to remove thousands of pounds of steel. We're stitching together multiple data sets. We're taking Meraki surveillance cameras that, yes, are surveillance, but they're also counting people. WebEx RoomKit camera to grab all the people count data in there. The Desk Hub is providing all of that capabilities from a people count standpoint. Everything we have here is 100% automated shading platform. We have sensors that are in the shade pocket, looking at light levels coming into this space. It's all now driven from software. We moved all the conference rooms off the walls. We wanted to be able to expose all of these great monuments for everyone to enjoy. Single Ethernet cable below, 90 watt PoE. that's powering the height adjustable desk motor, as well as the USB-C and USB-A ports.
There you have it, the tour of Pen 1, Cisco's new office space that they just redesigned. I hope you guys enjoyed this video. Thank you so much for watching.
And then I also encourage you to go to the CCCA website and look at their article that discusses going beyond 100 meters. It discusses a lot of the same points that I do and really drives those concepts home. So we know that PoE installations, they're efficient, they're reliable, they're safe, they use this equipment that we already know. We know that PoE, especially high PoE, can open us up to a lot of new applications. And getting those systems to work beyond 100 meters, it's possible with a balance of variables and making sure that you do your homework to make sure you get cabling and connectivity that has got good third-party verified data behind it. Thank you very much. Any questions? Yes, please.
Early on, you talked about the power savings with it. Is that to the switch or also from the switch?
What do you mean? Like the energy that was used?
Yes, where you talked there was a power savings using certain cables. The
The
loss.
Yes.
loss from the switch.
Yes.
Yep.
So is it, I get it to the switch will save you money, but how about from the switch? Does it give you more power from the switch?
So there's going to be loss in the system for every connection point and then loss as the signal travels down from voltage drop. Is that what you're
The
talking
heat.
about?
I think it was the heat.
Right,
Yeah.
right. So the 90 watts power saving on Cat 6A versus Cat 6, and then the 300, not watts, but 300, I think it was watts actually. No,
We're a bunch of shy people.
but no, I think that's what you're asking.
Yes.
That's from the switch to the end device that you're continuously saving that power.
Yes.
Right? Yeah.
Yes, from the switch to the end device.
Okay.
How much power does it take to operate that equipment?
Right. Is it how much the switch can also put out? So if I had 24 cameras versus 20 cameras
that's a good
on
question.
the out, going the other way as well.
That's a really important factor as well, and in our studies, because this is kind of Wild West. This isn't, the standards haven't written things out yet. So we're also seeing that some power sourcing equipment is not pushing out the power properly. So it's very important to make sure that you get reputable power sourcing equipment. Even a Cisco switch, which we know that Cisco is a very reputable, so in our labs we were doing some testing and we started getting some cameras that weren't working and we were like, we know these should work, we've done all this testing. We called Cisco and they were like, oh, sometimes we ship things that are not configured properly and we send them where they're configured at only injecting half the power that we guarantee. I'm like, why would you do that? So we actually had to call their tech support and get it configured to inject the right amount of power. So even with Cisco, but make sure that your power sourcing equipment is reputable so that it does push that power that it says that it will. Very important. And also y'all are very brave to sit in the front row because I'm like a karate expert here. Any other questions? Thank you for that one. Okay, thanks very much. Appreciate your time.